This screencast is going to explain the difference between theoretical yield and actual yield, and then show you how to mathematically calculate percent yield from those two values. So we're going to start off with theoretical yield, and theoretical is actually what we've been doing in class already, because it is based on a balanced chemical equation. So the analogy is if you make exactly how much the recipe says, so let's say you're making chocolate chip cookies and they say the yield is 24. Well, that is your theoretical yield. That's how much you could make if you followed the recipe exactly like they prescribed, and if you make the cookies the exact same size that they made them, then you can get 24. So that's theoretically how much you could make if you follow the recipe. You may make smaller cookies, and so you could get more than 24. Or you could bake bigger cookies, and then you wouldn't be able to get as many. So that would be your actual yield. That's how much you actually make in the kitchen. So if we kind of move from a cooking analogy to a chemical reaction analogy, theoretical yield is the maximum amount of product that can be made based on the amount of reactant. So the maximum amount of product that can be made based on the amount of reactant and the balanced chemical equation. So that's our recipe. Now usually we don't get as much as the recipe says. And there's lots of different reasons for that. I've listed a couple here. If you think about the what is stoichiometry lab that we did, where you took copper sulfate and reacted it with zinc and recovered the copper, most of you did not get exactly how much you thought you were going to get. So there's lots of different reasons. You can lose some of your product. There can be side reactions that are going on. Or you may not have converted all the zinc in this particular example over to copper. So some of you saw that in your beakers the next day. You had zinc mixed in with your copper as well. So the actual yield is what you actually make in the lab. So it's the amount of product formed during the chemical reaction. So I like to think of this one as like the lab or the experiment, whereas this is going to be more of a paper and pencil type of thing. So you're sitting there and drawing your little bridge and saying, well, how much could I make? Whereas this is, you actually went into the lab and you made it. Now the actual yield, like I kind of got ahead of myself there, usually these things don't all go perfectly. And so there's lots of different reasons that usually your actual yield is usually less than your theoretical. Now you can end up with percent yields that are greater than 100, but typically they're less than 100 due to loss of product and different things like that. So now that we know kind of the difference between these two, this is what's actually going on in the lab versus this is pen and paper, using our little bridges and figuring out how much we can make. You can actually calculate what's called percent yield. Now a lot of times students confuse this with percent error. They're actually related to one another, and if you think about it this way, let's say you made a 94% on a quiz. Okay, that means that you got 94% of the material correct. Another way you could look at it is you missed 6%, right? So you would have a 6% error on that quiz. That's how much you got wrong. But of course we record the scores as how much did you get right. Well, if you notice, there is a relationship between the two. When you add your percent yield to your percent error, they do sum up to 100%. So sometimes students, just always do percent error, and then they subtract from 100, and then that way they can get their percent yield. It honestly doesn't matter to me as long as you're showing that you understand what both of those terms mean. All right, so we'll start with some baby examples. So zinc reacts with copper sulfate. This should look familiar because it's the lab that we did in class. Zinc was set up as the limiting reactant in that case. We had plenty of excess copper sulfate, right? This says if we started with 1 mole of zinc and an excess of that. So a little different. It's not starting with grams like it did in the lab. It's saying 1 mole. How many moles of copper would we expect to produce? And then what is this in grams? Okay, so we start with our 1 mole of zinc. We don't have to worry about the copper sulfate because it's in excess. And we see that the mole-to-mole relationship between the zinc and the copper is 1 to 1. So if I have 1 mole of zinc, I'm going to make 1 mole of copper. So to answer their first question, I can make 1 mole of copper. Now to turn that into a mass, you guys know we've got to use the molar mass. They're a little loose on sig figs here. Let's just assume that that's an exact number. So then we would make 63.5 grams of Cu, just that molar mass from the periodic table. So none of that is new material. This last part is where it's the new stuff. It says if we actually yielded this many, so they've got a pretty nice balance that's measuring to 3 decimal places. So this is your actual. Then calculate the percent yield of copper. Well, how much should we have made? Theoretically, right, from the balanced chemical equation, as soon as you see that mole to mole, you know this is a theoretical because you're using the balanced chemical equation. We know that we should have made 63.5. So that one goes in the bottom for the theoretical. And then on top, you put how much you actually made. Okay? And to turn it into a percent, we just multiply by 100. So you get 92%. And that's a pretty good yield in lab. That would mean that your percent error was just 8%. So that's a very good yield for lab. All right, so we're going to try some of these examples. We'll go through as many as the screencast will let me record, up to 15 minutes. And then you'll have some practice that you can do to make sure you've got this down. Again, the stoichiometry part of it is not new. It's honestly just the calculation at the end to get percent yield. All right, so this first chemical reaction talks about hydrazine and hydrogen peroxide being used to fuel rockets. So it's highly exothermic. We haven't really talked about that a whole lot. Our next unit is going to be on energy, and we will. So this is just saying, hey, it gives out a lot of heat. If we started with 5 moles of the, and disappeared there, 5 moles of the hydrazine, and an excess of, so that means we don't have to worry about the hydrogen peroxide, how many moles of nitrogen would be formed? Okay, so looking at this equation, it's balanced. I'm going to go from moles of hydrazine to moles of nitrogen, and their mole-to-mole ratio is just 1 to 1. So 1 mole of N2H2 will produce 1 mole of N2. All right, so we get 5 moles of N2. And then it goes on to say, well, how many grams is that? So remembering that it's a diatomic, we've got to double that molar mass. So we're going to do 5 times 28. Again, sig figs are a little loose because of the type of numbers they're using. We'll just assume that 1 or the 5 that they gave us is exact. So about 140 grams. So again, sometimes students think, oh, is that theoretical or is that actual? And a lot of times, if you keep reading, you'll see. But anytime you use this mole-to-mole conversion, that means this is theoretical. That's how much you should have made. That doesn't mean you necessarily made that much. So down here it says calculate the percent yield. So they actually made this much. So this, they went into lab and they actually made that much. So that goes in the numerator. We should have made 140 if everything went perfect in this recipe. And then we'll turn it into a percent. So this comes out to 81% yield. Again, not great for the yield, not awful either for this exothermic reaction. All right, on this second one, it says carbon dioxide is released into the atmosphere when you burn C8H18. So you guys are experts now in writing combustion reactions. So we need oxygen, it's going to produce CO2 and water. We're going to balance it alphabetically. We end up with an odd number of oxygens, and there's no way for that to be odd, so I'm just going to go ahead and double it. So now if we go in alphabetical order, so we've got 16 carbons, we have 36 hydrogens, and a whole lot of oxygen. So over here, we've got 16 times 2, so that's 32 oxygens plus 18 more. So we have 50 oxygens on this side. That means we need a 25 there. All right, so got the recipe. It says if 3 moles of octane were combusted, so 3 moles of C8H18, how many moles of CO2 would be produced? So there's our question mark. They don't mention anything about O2, so we get to assume we've got plenty of oxygen. We don't have to worry about limiting. So the mole relationship between the two, for every 2 moles of octane, it's going to produce 16 moles of CO2. Okay, so that means we're going to make, theoretically, 24 moles of CO2. How many grams is this? And guys, if they weren't breaking this up into like moles and grams, we would just keep that bridge going. They've just broken it up, but we could certainly handle that in one long bridge. So now getting this into moles, I just find the molar mass of CO2. You get about 1,100 grams. So again, is that theoretical? Is that actual? Well, we've got a mole ratio right there, so that means this is theoretical. Anytime you use a mole-to-mole ratio, that's theoretically how much you could make. We go on to read, it says, if 873 grams were actually produced, calculate percent yield. So the actual is 873, the theoretical is 1,100, and we're going to turn that into a percent. And divide that out, we get about 79% yield. Okay. All right, and this last one, we've got a decomposition reaction. So calcium carbonate, so CaCO3, tells you it breaks down into calcium oxide, so Ca2 plus O2 minus makes CaO, and carbon dioxide. If 2.4 moles decomposes, so we don't have to worry about limiting, well, kind of do. CaCO3 is the only reactant, so it's going to limit. How many moles of carbon dioxide would be produced, and how many grams is this? How about we just go all the way to grams? So it looks like this is balanced. O's, we have 3. Carbons, we have 1. Yeah, everything's balanced. So for every 1 mole of CaCO3, I'm going to produce 1 mole of CO2. So that intermediate answer there would be 2.4. And then go ahead and get that into grams. We've got 44 grams in a mole. So that means we get 110 grams of CO2. Is that theoretical or is that actual? Well, we see that mole-to-mole ratio there. So this is theoretical. That's how much we should make if everything goes perfectly. They go on to tell you, well, we made 65.4 grams. So that's our actual. So what is the percent yield? So 65.4 grams on top, 110 grams on the bottom, multiply it by 100 to turn it into a percent, we get 59% yield. Okay, so our reactions on this backside kind of went from better to worse as far as our percent yields go. Alright guys, so that's all you need to know for theoretical and actual yield, and then how to calculate percent yield.